This is the Prelab video for the microwaves experiment of Physics 2213. And the one thing you'll notice as soon as you come into the lab is that the apparatus that you'll be using is quite large. And so you'll be working in groups of 4 rather than groups of 2. You'll notice that the center barrier between 2 neighboring optics tables has been removed so that this apparatus has all the space that it requires. Microwaves are generated in a certain type of microwave generator and coupled to free space using a microwave horn. The generator is this device, and it gets turned on simply by plugging it in. The receiver, which will measure the microwave power at a given location, looks very similar to the generator, and it's this guy. And you can tell it's the receiver because it has a meter on the side. And the meter tells you the intensity of microwaves that are going into the receiver. It has different scale settings and different sort of calibration factors. You're instructed in the lab manual on how to set that up properly. If you wish, rather than looking at this analog signal, you can take the output of this and put it into your digital multimeter and look at a digital signal. The absolute value of the signal measured by the receiver is never going to be important. What's going to be important for you only is the relative value. The apparatus laying down on the tabletop is this cross, and it comes in 2 parts. The first part is just a straight 90 degrees. The second part has these 2 arms sticking off, and those are rotatable. So if you had to change the angle, and you can measure what angle you're at with respect to some reference. And this arm is also rotatable. The first part of the experiment is to understand how the receiver and transmitter work. Right? In some sense, you can think of them as lasers. They're shooting out a beam in a particular direction. They are directional. But the wavelengths of microwaves are much longer than the wavelengths of lasers. And these don't end up forming nice narrow beams. They end up sort of coming out in some expanding sort of pattern. And so your first goal is to measure that pattern and to see how directional these devices are. One of the things you can do is, one of the things that you'll have to do is rotate the angle. You'll notice that this is a rectangle, it's not a square. And you'll investigate what happens if you rotate this by 90 degrees. What you effectively end up doing is changing the polarization of the electric field. And so to rotate this, there's a little screw on the back that you just loosen gently, rotate it, and then tighten that screw again. Okay. So the first part of the experiment is, well, as I say, there's several investigation experiments to figure out how the apparatus works, how to work with these different the system that you'll be using. I will note that these are magnetic, so they stick to our optics tables, which is kind of nice, that things don't move around. But in some cases, they stick reasonably well, and sometimes it's kind of hard to unstick it. But it's just a magnet, so don't be afraid to just, pull on it as hard as you need to. Once you figure out how microwaves work, and understanding that microwaves are just electromagnetic waves, just like visible light, you're going to end up, your task is to build a Michelson interferometer. And once you build a Michelson interferometer, you'll then investigate what the wavelength of these microwaves are using your Michelson interferometer. Now, of course, we're not going to tell you how to build a Michelson interferometer because you just built an optical one last week or recently. And so it's your goal, using these various other components, to design and build the interferometer. And so you're given a bag that has a whole bunch of different things. Pieces of metal, something called a partial reflector, polarizer, different reflectors, partial reflectors. And when you want to use these, they get mounted on to these what are called component holders. And it's just that easy. There's magnets here, and these, whatever component you want, will just stick to those magnets, and then they can get mounted onto our system. Notice there's this little cutaway here and this little groove here And that's just for mounting on these arms, and it'll be kind of self-explanatory how to do that, so that those get mated into that. The beam goes through the component holder base, so you can measure precisely what position you're in. Okay, so you're given all the components required. There's different component holders. Well, they're all the same, but there's a number of them depending on what you want to do. And your goal is then to determine what the wavelength of these microwaves are by building a Michelson interferometer and doing what needs to be done to measure the wavelength. And so, of course, when you're finished, you'll clean up all the components and put things back the way that you started. So this is a fun experiment. It's the only non-laser experiment that you'll be doing, but the point is that microwaves are electromagnetic radiation just like lasers are. And so all the same principles and all the same techniques apply. Good luck.